Hello world, it's Siraj and neural ordinary differential equations. I know that sounds complicated, don't go anywhere, but it's a very important idea. And guess what? The biggest AI conference of the year is called NeurIPS. It just happened last month in December of 2018. Over 4,854 research papers were submitted to NeurIPS. That's a lot of research papers. And this paper that I'm about to explain to you in detail right now won best paper. It was one of four that won the best paper out of over 4,854 research papers. People from NVIDIA, researchers from Google, researchers from Facebook, all of these big tech companies submitted their best work, and this paper was one of four that won the best. And I'm gonna explain to you how it works in this video. Now, why should you even care? This is a demo of the paper behind me, by the way, so you can see there's a lot for me to explain here. But why should you care? Let's start with that. This idea can be applied to time series data. What is time series data? Any type of data set that depends on time. So what would be an example? Finance data, right? How do stock prices change over time? Healthcare data. How do patients' biometric signals change over time? Anything that changes over time, can be considered time series data. Time is an important element, right? This technique can make predictions on time series data better than recurrent neural networks, which is kind of the de facto go-to type of network to make predictions with time series data, including all variants of recurrent neural networks, including residual networks. There's so much theory there. Dense networks, highway networks, there's a lot. But we have something to focus on in this video. It's called neural ordinary differential equations. Okay, so let's get started with this. What even happened here, right? So of all these papers, this is the one that got the best paper award. So what is the basic idea before we talk about calculus? That's really what I'm hyped to talk about today, calculus, because this is using integral calculus. Instead of differentiating, we're gonna integrate. If you don't know calculus, don't worry, I'm gonna try to put that prerequisite knowledge into this video as well, because I want this video to be for everybody, not just for researchers, not just for AI enthusiasts, but for everybody, even if you've not coded before. So let's see how well I can do this, okay? So here we go. So here's the basic idea. Neural networks are function approximators. Neural networks are a series of matrix operations. So there are a series of operations, right? Like add, subtract, multiply, divide, that we apply to matrices. Matrices are groups of numbers, right? So we have an input matrix, we apply these operations to it, and then we get an output, and this output is the prediction. And so the way we think about these neural networks, this is a picture, by the way. The way we think about these networks is we group them into what are called discrete layers. So layers are in the network, they're just a block of operations. And so we can actually make a rap song out of this, right? So input times weight, add a bias, activate, repeat. Input times weight, add a bias, activate, repeat. And so we just keep doing that over and over and over again. Input data times the weight matrix, add a bias, and then apply that to an activation function, which could be several, and then we just repeat that over and over again, and then we get the output, right? So what this image shows is a neural network, okay? And it shows the matrix operations that are occurring. These lines represent multiplication operations applied to all of these numbers such that we get the next layer. So this idea of layers is very persistent in neural networks. Neural networks have layers, right? So that's the basic idea of neural networks. So what this paper does is it says, instead of having these be discrete layers, that means, we have one layer, and then we have a second layer, right? It's individually independent grouped layers, blocks, right? Just separate, discrete. Instead of doing that, let's consider a neural network as a continuous function. That is a function that is both infinitesimally big and infinitesimally small, right? This is a continuous function, right? There's no grouping, there's no blocks. It's just one function, forever within, forever without, right? In one direction. That's a little inside joke for people who follow my channel regularly. Subscribe, by the way, because I promise you, you're not going to be getting this kind of lecture anywhere else. Subscribe. Okay, so here we go. That's what this paper does. It groups neural networks into this category of continuous functions. So instead of having single layers, we just have the entire network be one continuous block of computation. And what this means is no more specifying the number of layers beforehand. Normally you have to decide how many layers do I want my neural network to have, right? And once you do that, then you can build the network. But with this idea, instead of specifying the number of layers beforehand, we specify the desired accuracy, and it will learn how to train itself within that margin of error. Now, this is still in the early stages, by the way. The team, it's at University of Toronto, at the Vector Institutes. They are still working on this, and it's not perfect. It is a research paper. It wasn't meant for production, but it is a very promising direction for 2019 for AI. And I think that all AI enthusiasts should read this paper, or at least watch this video. So direct them to this video, because this is going to be easier than reading the paper, which was, I had to review quite a lot of integral calculus, but that was a lot of fun. Okay, so why does this matter? Time series data is why that matters. Okay, so why does this matter? Because it means faster testing time than recurrent networks. So just faster neural networks if we do it this way. Instead of considering our network as discrete blocks of discrete layers, we consider it as a continuous function. And once we do that, we can have faster testing time. So we're making a trade-off between precision and speed. It also means that we get more accurate results for time series predictions, i.e. continuous time models. What can be considered time series data? Tell me. Finance, right? How do stock prices change over time? Healthcare, how does a patient's biometric data change over time? How does what change over time? All of that is time series data. And the thing about neural networks is that with these discrete layers, they expect the intervals for these time series data sets to be fixed, right? So these are predictable fixed intervals. Every day we're taking a recording, or every hour, or every second. But that's not how the real world operates, right? So one example would be healthcare. Patients and hospitals aren't always regularly recording a patient's biometric, data, every hour or every day. It's irregular. And so neural networks are bad at predicting are bad at predicting an output for time series data that is irregular. But this is a promising direction. This ODE network, which is Ordinary Differential Equation network that these guys have invented. And one more point. Why else does this matter? So 2 points I've already talked about. Faster testing time and more accurate results for time series predictions, i.e. continuous time models. And the third point is this opens up a whole new realm of mathematics for optimizing neural networks, right? If we frame it as what's called a differential equation, which I'm going to explain, don't worry if you don't get that, which I'm going to explain. If we frame it this way, as a continuous differential equation, then we could use, instead of gradient descent, which we're used to only, we can use an entirely new class of optimization solvers, which are called differential equation solvers. And there's 100+ years of theory behind these that we haven't really applied to neural networks yet in a mainstream way. So there's a lot of promise there. Lastly, we can compute gradients with a constant memory cost. So every time you're adding layers to your network, you are linearly increasing the amount of memory that it's using, right? But with this idea, you have a constant memory cost. So in this video, the concepts that we're going to cover are basic neural network theory, residual neural network theory, ordinary differential equations, then ODE networks, Eulers method, the adjoint method, and then we'll have a conclusion. So that's a lot. So sit down and enjoy. This is going to be amazing. Here we go. So neural networks are popular types of machine learning models, right? Neural networks are built with linear algebra, meaning they are matrices with matrix operations, and they are optimized using calculus. Calculus is the study of how things change over time. It's used in physics a lot. We'll get into this in a second. So neural networks consist of a series of layers, which are just matrix operations, and each layer introduces a little bit of error that compounds through the network as we propagate forward. So that's one diagram. Now here is a more mathematically accurate diagram of what's happening in a neural network. We have our input data. This is a lot. So we have our input data, right? This could be image, video, text, whatever it is. And then what we do is we take that input data and we multiply it by W. W is the weight matrix. And so we take the input data, we multiply it by our weight, we add a bias, B, see this, B, and then we activate. Okay, so F is the activation function. So look right here where my mouse is circling around. We have our input data, which is P, times the weight, add the bias, and then take the result of that, the sum of that, and apply this activation function to it, activate. And that is the output of the first layer. We take that output and we feed it into the next layer, and we again do it again, and we do it again. So we could think of a neural network as one giant composite function of functions within functions. So the output is going to be a function of a function of a function of a function for as many layers as there are. And so in terms of code, here is our activation function. It's a sigmoid function, a nonlinearity. I have a million videos on how neural networks work, so I'm not going to go into that in detail right now, but just basic idea. We have our input data, we have our labels, we want to find the mapping between both, and so for our training loop, we perform forward propagation, input times weight, add a bias, activate. And then we compute the partial derivative of the error with respect to our weights and then propagate that backwards. That's back propagation. Google or YouTube Siraj back propagation in 5 minutes to see how that works. Okay, now let's get into this. So the idea is that to reduce compounded error, let's just stack more layers, right? It's more layers. The more layers, the deeper the network, i.e. deep learning. And so is this your machine learning system? Yes, you just pour the data into this big pile of linear algebra, then collect the answers on the other side. What if the answers are wrong? Just stir the pile until they start looking right. That, in essence, is how deep learning research goes. Let's be real, everybody. So there's a lot of theory behind how many layers to add to your network, but the basic idea is that the number of layers deeply affects the output of the network. Too few could cause underfitting, so meaning your line won't fit the data. Too many, and it could cause overfitting, meaning your line will overfit the data. So you want to get it just right so the line perfectly fits your data set. So neural networks, all this stuff, it's glorified line fitting to data in a way. So there's so many different rules of thumb for how many layers you should be choosing. You know, here are 3 bullet points, here are 3 examples. And so when we use a higher level library like Keras to build a deeper network, right? So let's say we'll build an LSTM network in Keras right here. And so for each line represents a single layer. If we wanted to make this network deeper, then we can just say model.add LSTM, and then 32, or however many dimensions we want it to have. And so we could just keep on stacking them like this. Stack, 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 blah, blah, blah. You see what I'm saying? We keep on stacking them if we want it to be deeper and deeper. And so there's a threshold here where adding more isn't going to do anything. So a solution to this was proposed by Microsoft. By the way, Microsoft, you guys are killing it. Like, let's go. I'm proud of you guys for just being super open source and, you know, Onyx and all this stuff. So keep going. So in December of 2015, Microsoft proposed this idea of what are called residual networks. Okay, and so they won the ImageNet classification competition using these residual networks. And residual networks had the best accuracy in the competition. So if we look, they beat Google, they beat everybody. These were the results. And so this is Microsoft right here. And so the smaller bar is better because it means a lower error. Okay, so ResNets beat everything else. And they had the best accuracy. And what they were able to do is they were able to train networks that were up to 1,000 layers deep while avoiding vanishing gradients, meaning avoiding that lower accuracy that occurs with deeper networks. And 6 months later, their publication already had more than 200 references. That's a big deal. So people really like this idea. And so the way residual networks work, very simple, really very simple. Like, it's just too simple. You know how we just keep feeding the output of the previous layer to the next layer? So the only change we're making for residual networks is we're not just feeding in the output of the previous layer, we're feeding in the output of the previous layer and the input of that layer. So we add that. So f of x plus x, and that's what we feed into the next layer. And then we do that again and again and again. And so what this does is it creates these skip connections where we're not just feeding in the output of the previous layer, we're also feeding in the input of the previous layer to the next layer. So the network can decide how deep it wants to be. So this is an example, right? So ResNets versus, you know, other types of networks. So instead of hoping each stack of layers directly fits the underlying mapping, we can explicitly let these layers fit a residual mapping. So we cast it from f of x to f of x plus x, okay? So it's very simple, like I said. So we add the output of the activation function, which is f. So x is the input. So x would be the input to the network. F of x is going to be the activation function applied to x, and then we add x again, and that's going to be the output that's going to be the output and also input for the next layer. Okay? So where f is the function of the kth layer and its activation. So this is the formula for a residual network right here, okay? This is what's going to act as the input to the next layer. Not just the output from the last layer, but the input from the last layer. We add both. That's it. That's it. Now, here's the cool stuff. So, what if we recast this equation by just adding in some constant? Let's say the constant is 1, right? There's already a constant 1. We can't see it. But let's just name it some letter. Let's name it H. We could name it anything. We could name it V. We could name it Q. But let's call it H. And let's say H equals 1. So we know that H equals 1. And we'll say 8. So we'll add it to our equation. So our original equation is x equals x plus f of x. So we'll just add h in there. So it's x equals x plus h times f of x, where h is 1. So it doesn't really do anything. It's just there. And it's still true. Now, why did we do this? Because if we cast it in this way, this equation right here, x equals x plus h times f of x, is the formula for what's called Eulers Method for solving ordinary differential equations when h equals 1. So you might be thinking, what are you talking about? What is Eulers Method? What are differential equations? And what do they have anything to do with neural networks? So hold that thought. Let's look at some code first. Okay, so this code right here is a normal layer. Okay, this is a normal layer in a convolutional neural network meant for image classification, right? So we have a normalization, operation, activation, convolution. Normalization, activation, convolution, right? So let's modify that to be residual. What did we change? We captured x, the input, and we set it to res, because we want to use that in a second. And so remember, x is the input to this layer, and we're also, when we give it to the next layer, here's the other difference. We're giving it the output of the activation function and the input, and that's what we feed to the next layer, right? So this is the difference, these two lines right here, okay? So back to the question, I just want to show you that. What is the significance between residual networks and ordinary differential equations? Okay, so a differential equation is an equation that tells us the slope without specifying the original function whose derivative we are taking. Let's just go into this, okay? We've got some calculus. So if we have a function, right? We have any kind of function, sine, cosine, x cubed plus 7x, any function, if we graph it, if we graph that function, it could do this, it could do this, it could do this. If we want to find the slope of the tangent line to any point on that function, that slope is the derivative, okay? The derivative of the function f of x evaluated at x equals a at any point gives the slope of the curve at that point. Why does this matter? Because if we derive a function at any point, it gives us a slope, and that slope tells us the direction that that function is moving at that specific point in time. Now, that's the derivative. Now, so any function we can compute the derivative of, right? So x squared, the derivative is 2x, because what do? We take the power 2, we move it to the coefficient, and we subtract 1 from that power, and that gives us the derivative. It's that simple. So x cubed, 3 to the x, and then we do 3 minus 1 is 2, so 3x squared. So x to the 4th, the derivative is, don't look, 4x cubed. I'm not even going to look now. X to the 5th, 5x to the 4th. Okay, 6 to the x to the 6th, 6x to the 5th. Okay, that's the derivative. And we use a derivative a lot in machine learning, right? The derivative helps us compute the gradient that tells us how to update our network. But what we don't use a lot are integrals. Now, the integral is the opposite of the derivative. So assume that we have the derivative and we want to find the original function. How do we do that? How do we go from the derivative back to the original function? Well, we just do the reverse. We take that coefficient, we put it in the power, right? The exponent. And that gives us, and that's called integration. So taking a function, finding the derivative is called differentiation. But taking the derivative and finding the original function is called integration, where we're using the integral. And so this is a symbol for the integral right here. So differential equations, okay, there are two types. There's ordinary differential equations and there are partial differential equations. So ordinary differential equations involve one or more ordinary derivatives of unknown functions, whereas partial differential equations involve one or more partial derivatives of unknown functions. So the idea is that in an ordinary differential equation, we are taking the derivative of one independent variable, whereas in partial differential equations, we're taking the partial derivative, so there are multiple independent variables, right? We are differentiating with respect to one of those variables because they're all independent, but in an ordinary differential equation, there is one independent variable. So we want to solve the differential equation. So what a differential equation does is it sets the derivative equal to some value. It could be, dy dx equals f of x plus 3, right? So it gives us that. So we set the derivative to some value, right? So let's say, here we go. Here's a perfect example. If we have some function, right? Some function in the world, we want to find the derivative. And we say that derivative plus some random number like 3 or 4 or 5 equals 1. That's a differential equation because we can use a differential equation solver method like Eulers Method, which we'll get to, or some other method, to then find the original function. So the whole point of all of this, of partial, ordinary, all of this, is to find the original function, to approximate the function. And in general, that's what we're doing in machine learning. And in general, that's what we're doing in science and technology and math and everything, is we are trying to find the function. And the function tells us everything. The function tells us everything. Math tells us everything. Not to get too poetic here. So we use this a lot in physics, right? So if we have ideas, if we have concepts like displacement and velocity and acceleration, if we take the displacement and we differentiate, we get the velocity. If we differentiate that, we get the acceleration. If we take the acceleration and we integrate that, we get the velocity. If we integrate that, we get the displacement. So you see what I'm saying? It's very useful in physics and in these different fields to both differentiate and integrate. So I'm going to bring this back into machine learning. So one more example, 2x has several possible integrals, and it has one derivative, all of these expressions. So here's an example of a differential equation, right? So we have some derivative right here, right? dy dx equals x plus y over 5. Okay, and so what we do is we say, let's take that derivative and compute the original function using this ordinary differential equation solver, and that will give us our solution. So this resulting graph, let me just compile that. This resulting graph is our original function. So all we knew was a differential equation right here. And using an ordinary differential equation solver, we were able to find that original function. Now, let's apply this to ordinary differential equation networks. Now consider a very simple ODE, we'll call them ODEs from now on, okay, that's what it stands for. Consider a very simple ODE from physics. So let's say we want to model the position of a marble. Let's say we have a marble, right? And we just want to roll it on the floor. We're going to roll this marble on the floor. And what we want to do is we want to predict where its position is eventually going to be using its velocity and using time. So these are the three variables that we are considering here: time, velocity, and position, okay? And so we can model the relationship between these variables using this function. So we can calculate its velocity by differentiating its position. So the derivative of the position is its velocity, and we can represent that using this equation right here. So Eulers method solves this problem by following the physical intuition. So a position at a time very close to the present depends on my current velocity and position. So let's say we're traveling at 5 meters per second. Okay, we're traveling at 5 meters per second and we travel for 1 second, right? So if we're traveling for 5 meters per second and we travel for 1 second, how far have we traveled? 5 times 1 second, 5. We've traveled 5 meters. And so we can model this using this formula right here, okay? So the position is going to be equal to where we currently are, x of t, plus h, the velocity, times the derivative of the position. And that's going to give us, so it's going to be 5 times the number of seconds we've been traveling, plus wherever we were previously, okay? But since we know that x prime of t equals f of x, we can rewrite this initial equation as this, okay? So x of t plus h is going to be equal to the current position plus the velocity times the number of seconds that we've traveled, okay? So we are computing how far we're traveling by taking wherever we're starting from, and then taking that starting point and adding how far we've traveled by multiplying the velocity by the time that we've traveled. And so what this looks like then, if we squint at this, it looks at, this is the formula for Eulers method yet again, which also looks like the formula for residual layers. So we are connecting physics to neural networks by framing the residual network equation as a differential equation, just like we did in physics. So differential equations can represent neural networks. Neural networks can be represented as differential equations. So what does this mean? It means that we can create new models for optimizing these networks using different numerical approaches to solving ordinary differential equations, which there are over 100 years of theory behind. Over 100 years of theory are behind ODEs, and we haven't applied any of that to neural networks in general. I mean, there's some papers. I mean, there's, it's not in a mainstream way. We haven't seen anything in production like this. And what this means is it is the possibility of creating arbitrarily deep neural networks. And training of these deep networks can be improved by considering the so-called stability of the underlying ODE and its numerical discretization. So 2 more points. To create these arbitrarily deep networks with a finite memory footprint, we design these neural networks based on ODEs. And so gradient descent, the optimization technique we all know and love in neural networks, the most popular optimization technique, can be viewed as applying Eulers' method for solving ODEs to gradient flow, which is right here. It can be represented right here. So you might be thinking, so what's the difference here? If we're not applying it to gradient flow because there are not discrete layers, it's instead a continuous function, what then does an ODE net look like? So an ODE is a function that describes the change of some system through time. Thank you, calculus. Right, we're using the derivative to find the original function. And in this setting, time is a continuous variable. Now imagine neural networks as this continuous system. So what happens then if we do that is that time really, it becomes something more like the depth of the network. And note that there are usually a discrete number of layers, but in this case, there's a continuous number of layers. So we can either think of this as having weights that are a function of the depth, or as having shared weights across layers, but adding the depth as an extra input to F. So anywhere you can put a residual network, you can also put an ODE network, and each ODE block can be used to replace a whole stack of res blocks. In fact, they had an example in using the MNIST handwritten character dataset as an image classification example, and they replaced 6 res blocks with 1 single ODE block. So again, traditional deep nets, input to a layer gives us the hidden state. Hidden state goes to the next layer, gives us the next hidden state. Hidden state goes to the next layer, gives us the next one. ResNets, we do the same, but we add the original input. Okay, that's how that works. So if we model our networks like this, we can use ordinary differential equation solvers like Eulers' method that solve the trajectory of a system by taking small steps in the direction of the system dynamics and adding them up, which allows for better training methods. Okay, so let's cover Eulers' method just one more time. So the blue line represents the function, right? And so what we want to do is we want to approximate this function. So what we do is we say, okay, let's take this first point on the line and find the derivative of it. Okay, it's going to give us a tangent line. And we take a small step in that direction. And then we say, let's do it again. What is the derivative of the function? Okay, and let's give us another tangent line and another one and another one. We just keep doing that over and over and over again. And so what we can do is we can roughly approximate what that function is by continuously deriving the points on that line, and that's Eulers' method. And so it's going to give us a rough approximation. So Eulers' method isn't that great. It's a very primitive solver, but the point is to show that we can frame these networks as differential equations. And so what happens is in a residual network, there's a discrete sequence of finite transformations, whereas in an ODE network, there is a vector field which continuously transforms the state. And so this represents the difference between them, their vector spaces. Right? And so there have been over 120 years of developments for efficient and accurate ODE solvers. Let's apply those to neural networks and see what happens now. That's the next step here. So how then do we solve this thing? If we frame a neural network as an ODE, how do we solve it using an ODE solver? Do we use Eulers' method? We could, but we could use a better one. Instead, let's use what's called the adjoint method, which dates back to 1962. Okay, it's like an instantaneous analog of the chain rule. Okay, so the thing about the adjoint method is that there is not a lot of content, if any, about it on the internet that is accessible. So I'm going to do the best that I can to explain this. And I myself need to continuously learn about this. And even the authors of this paper are still figuring out how this is going to work. But they believe, and a lot of people believe, and I think that this is going to be as big as GANs were, generative adversarial networks. Okay, so the adjoint method. So the basic idea is this. We are computing three integrals. Okay? So we're computing the adjoint, which captures how the loss function changes with respect to the hidden state. That's one. We're computing the hidden state backwards in time together. And then a third integral tells us how the loss changes with the parameters theta, which are the weights. So there are three integrals, and we combine these three integrals into a single call to an ODE solver, give it to that. It's going to concatenate the original state, the adjoint state, and the other partial derivatives into a single vector, and that will then solve our equation. So here is what the algorithm looks like. We compute a gradient with respect to the time, or t, whatever t is going to be. We define an initial augmented state, then we define the dynamics of that augmented state, concatenate the time derivatives together, solve the reverse time ODE, and then return the gradients and then update our weights. Okay, so that's quite a lot. But in the code, let's look at some code. This ODE solver was applied to the forward propagation of the network. So they have a code that's applied to time series data, they have code that's applied to MNIST, they have several code examples. And so I've actually even, I've downloaded the code and we can run it right here. Super easy, just need to install PyTorch. And what it's going to do is it's going to approximate this function using a continuous neural network, an ODE network. And it's using an ODE solver to forward propagate the data. It's still using gradient descent, but it's using this ODE method to forward propagate the data. And it's approximating what this line looks like. And so we can see how it's approximating both the trajectory, a different version of that graph, and then the learned vector field. And it's training over time. Okay, but so I just want to show that as an example. Okay, so you can run this code, and I've got the code, it's like right here. Okay, but I took out all of these like unnecessary bits just so for learning purposes, and I've written it here. So let's just go through this. Here's a normal residual block, right? We already looked at an example of this before, but here's a normal residual block. Activation function, downsampling, convolutional network, forward pass, right? That's a normal residual block. Now here is an ODE function. So what we do is we are, again, defining these neural net layers, convolution, normalize, activate. And then we are, again, normal forward propagation looks very similar to a regular neural layer. Now in the ODE block, we encapsulate that function, so we call it ODE funct. And then in the forward propagation method, here is our ODE solver right here, the adjoint method, which they created in PyTorch, by the way. Check out their library. And we input that ODE function to this solver for forward propagation. And that's really the key difference right there. And so in the main method, we add these pooling layers. And so we say, okay, here are our layers. It's going to be a single ODE block that's given this ODE function. Let's have a fully connected layer at the end and build our model. Our model is a sequential model consisting of these downsampled layers, our feature layers, which is our single continuous ODE block, and then our fully connected layers at the end to output that prediction. And then we go on as we normally would. We declare our gradient descent optimizer, which is going to be stochastic gradient descent. We initialize our training data. We apply our training data to the model. We get our prediction. We compute our error. What's the difference between the prediction and the actual? And we backpropagate using the optimizer. And that's it, right? So that's the difference here. So let's summarize what just happened here. Neural networks are a popular type of ML model. They're built with linear algebra, matrices, and optimized using calculus, gradient descent, all these different solvers. They consist of a series of discrete layers, which are just matrix operations. And each layer introduces a little bit of error. To get around this error, Microsoft introduced residual networks, which is that skip connection idea. F of x plus x equals the input to the next layer. And so what the researchers found was like this equation for a residual network resembles an ordinary differential equation. So why don't we use ordinary differential equation solvers like Eulers Method or the adjoint method to then solve a neural network and instead have continuous layers? And when they did that, it actually worked and it had a better prediction result than a recurrent network did for approximating this function right here. And what happens then is we can apply it to irregular time series data in the future to have better predictions. We can have faster testing time, and we can apply a whole new class of mathematical operations that are dedicated to ODEs, to neural networks, and that just opens up a whole new branch of AI possibility, which is amazing. And we can compute the gradient with a constant memory cost. Instead of constantly stacking layers, we have one continuous ODE block. Okay, so I hope that made sense. I hope that excited you. I've got links to everything that I've talked about here and helpful links in the video description. Subscribe if you haven't yet. Thank you for watching. And for now, I've got to go make some more videos and plan my course and music video. So thanks for watching.